All right, you guys glad it's Friday? Oh, well, some of you are. I am, especially since last night, I don't know, I had it in my head that it was Friday. So when I woke up this morning, I was like, oh! Here we are. Before I forget, don't come to class Monday. I won't be here. And I hope you guys won't either. It's a holiday. There's no classes. Right? You knew that, right? I was hoping I got one head nod. It's always good to confirm, so if I don't show up, you're not going to show up. All right, we'll get on with it. I'm looking at the PDF calendar that's on WebAssign that I made for you. So we've covered Chapter 1, 2, 3, and I'm finishing 4 today. Or actually, we pretty much finished it, but I'll be discussing a few things. And starting Chapter 5. So Monday is a holiday, but remind you, you have your third homework assignment due Sunday on Chapters 3 and 4. And then no class. So when we meet back up next Wednesday, we'll finish Chapter 5. Then on Friday, we get to review everything. So the week after that, on Monday, we'll have our first exam on just that stuff. I try to have exams a little more often instead of just like 2 a semester or 3. I mean, you guys will have 4, so you don't have to remember as much for as long. I hope you like it. And each test won't count as much then. So I know some people have really bad exam day anxiety. So, also, you guys have all read the syllabus, right? I hope so. That was the point of the first homework. But I keep getting email questions implying to me that people haven't read it. But something I want to emphasize that you should know then is the lowest homework score at the end of the semester I will drop. It's 2 reasons. One, something happens in your life and you can't make one, or you need to go to a wedding, or you missed one. It won't matter. As long as you do all the others, that won't count against you at all. Because I will drop your lowest. If you miss one, that's obviously your lowest. Another reason is you can do all of them, and it's kind of a way of extra credit. The lowest one won't count. Likewise, I do the same thing with the exam. If you bomb one exam, it's okay. I'm going to drop your lowest exam score. Or if you can't make an exam for whatever reason, that's why I do it. So maybe you'll have a little less anxiety on this first one. So that'll be on the 27th. Also, WebAssign, I think your free trial ends on the 20th. So by the time we meet next time, after your homework's due, anything going forward, if you haven't purchased access, you're going to miss. You can't do homework. So, just reminding you. Okay. Any questions about that? Alrighty. Well, let's do some clicker questions then. All right. So. I will connect to ResponseWare for you mobile users. Now we have that. Open polling. PowerPoint up. All right. In the lower right, you should see the session ID to log into ResponseWare. I'm still on channel 44 for you clicker users. Give you a moment to log in. And we'll do some check your understanding questions. How many of you are appreciating those in the text, by the way, at this point? They're called check your understanding questions in the text by Hewitt? Yeah, raise your hand. Okay, good. I'm glad some of you are. The rest of you, raise your hand if you don't know what I'm talking about. Okay. Is that because you haven't read the book or don't have a book? Well, they're in the e-book. It's in the chapters, reading. Basically, you go along and then he asks you a couple questions. You work a problem or some concepts to see. It's the same author. It's the same bank of questions that I pick and choose from or create some of my own and add them in. But those are great. That's how you know if you're getting this stuff. And so here's another session to see where we stand from your reading and whatnot. All right. I want number 20 I'm starting with. This one. All right, this one I hope is easy. Okay, polling's open. Force of gravity acting on a 2 kilogram melon is what? You guys remember how to do that? 2 kilogram melon. What's the force of gravity acting on it? What's up?
You press enter after you put the letter in?
You shouldn't have to press enter. When you push it, they either give you like a check mark or a smiley face if you have a display. And let me see yours because I got your email and I haven't seen any of your.
Well, I might not have done it right.
Okay.
So
Which one do you want to push?
C.
Okay, I want to watch. Just a second. Yeah. All right. And you are 280113. It's hard to do while I'm actually open. It acts like it is, so we'll check when we're done again this time. And okay, you guys had enough time. Closing the session here. All right. Most of you think it's C, but some of you think it's B. So, somebody that thinks C, tell me why. Is the force of gravity 9.8 something? It is 9.8 meters per second squared, but what does that value represent? So mass times gravity? Yeah, that 9.8 is a what? What would we call? Acceleration, good. So it's not the force, it's an acceleration. So we do have a mass, 2 kilograms. And if you want to change something's motion, you accelerate it. For this one, we'll use 10. It's close anyway. So 2 kilograms times 10 meters per second squared is 20 newtons. So that means its weight's 20. The force of gravity on it would be 20. So those of you that answered 10, is there still some confusion? Can I help? Make sense now? I know you might be embarrassed, but I want you to understand it. Okay. So yeah, just mass times acceleration gives you force. It's Newton's second law, that interplay. And if you're dealing with gravity, you use the acceleration due to gravity. So just mass 2 times acceleration of gravity, 10, you get 20.
Could you show the session ID again?
Yes. Oh, that stinks. Well, okay, there it is on the bottom right. I know there's a button just to pop it up, but of course I hit the wrong button and had to get back in. Tell me when you got it. Alrighty. Let me load up the next question then. Okay, polling is open now. So for a given force, how are the acceleration and mass related? So basically asking you, is there a difference? Are they the same thing? Are they directly proportional or inversely proportional? All right, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Meh. Okay, we're split between A and B. Most of you think it's it's proportional, but you're not sure if it's directly or indirectly, inversely. Directly means if one increases, so does the other. And inversely means if one increases, the other decreases. So, acceleration and mass. Let me write the formula and guide our thinking. Or, so, for the same force, that means this F's not changing. So if you increase M, what does A have to do? Go smaller to keep that the same. Or you see that it's on the denominator. This means they're inversely proportional. So it's B. Any questions? All right, polling open on this one. This one makes you think a little more. Your hint is the formula on the board. So you're pushing a cart, but now let's say you push it with twice as much force, but it also now has twice as much mass. So we've doubled F and we've doubled M. How is the acceleration affected? Oh, most of you are in, so 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay, large majority, 82% think it's C. Good job. So again, well, that's just like doing this. If you put a 2 here, and you put a 2 here because you've doubled both, do you see that the ratio is still the same? Just to emphasize again that you exert a force on something, it accelerates. That'll affect it directly. But you increase its mass, you've doubled its resistance, its inertia, and so it's going to resist you twice as much. And so those the two changes will balance each other out, and the acceleration would stay the same in that case. All right, polling open. What happens to the speed of an object during free fall? I should specify, since it's in your book, but we just covered it last lecture. Free fall is when something falls only under the influence of gravity. That's the only force acting on it. Thus, you're ignoring air resistance in this question. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Meh. Okay, you guys are split between A and B. It's either increasing or it changes by increasing amounts each second. So is it increasing the same amount of speed each second, or more? It's increasing by a larger and larger amount each time. And that can be confusing. Good. That's why I asked this question. So let's think about it. Let's take gravity. The acceleration is 10 meters per second squared, or 10 meters per second every second. Acceleration is defined as How would you say it? What's acceleration mean to you?
The initial speed, the end speed, divided by the time.
Yeah, the initial and final speeds divided by time. Good. You're mathematically thinking. That works. Conceptually, what that means is the velocity changed over a certain amount of time. So even just generically, yeah, acceleration is a change in velocity. So it's going to change 10 meters per second every second. So the correct answer is what? Come on. A. It increases the same amount each time. Remember, after 1 second, if it starts at rest from 0 meters per second, after 1 second, it will have accelerated up to the velocity of 10 meters per second. During the second second, it will increase its velocity by another 10 meters per second, and now be 20. And then another 10, and another 10. So when you have constant acceleration of 10 meters per second squared, the velocity will increase every second, but by that same amount. So you are getting faster and faster, but it's increasing by the same amount every second. Does that make sense now? Any concerns? So you know, if you time something and you see that it increases, let's say, 8 meters per second, and now it's 8 meters per second faster again, and 8 meters per second faster still. What's the acceleration? 8 meters per second squared. Yeah. If during the first second it increases its velocity by 2, then it increases its velocity by 3, and then by 4, and then by 5, what do you know about the acceleration? It's not constant. It's increasing also. Very good.
When it's not under free fall, then will we say it increases by the same amount until it reaches terminal velocity?
Yes, when it's not in free fall, what's it do? Describe its motion. I think I have a question, but this will be your hint. It starts accelerating, and then
air resistance.
but then air resistance starts acting up on it, causing it to do what?
To reach a terminal
Reach a terminal
velocity.
velocity, right.
So it increases by the same amount until then.
Under a constant acceleration, it would increase by the same amount. When you throw in air resistance, though, it's decelerating more and more and more. So the acceleration in that case would be changing. Let me draw it actually. So let's say you drop it, you're not moving, and then it falls, and you have some velocity. So the force on this is its weight down, but there's some air resistance on it now, right? Some resistance, air resistance. The net force is in which direction? Down. So it's still accelerating. At this point, what's its acceleration? 10 meters per second squared? Greater or less than? If you think it's less, raise your hand. If you think it's still 10, raise your hand. Greater? Okay, well, most people are saying less. This is 10 meters per second squared. But this is causing it to accelerate upwards a little. So the combined effect, that net force, is its weight minus the air resistance. So mg minus whatever the air is trying to accelerate it at. So you can think of that as the mass with some net acceleration. Did you follow this? Yes?
My thought was that if we drop something and it's not under free fall, it would accelerate, or it would change its speed by the same amount. Say if it's 10 meters per second first, for the first second it would be 20, and then 30, and then 40, and after 4 seconds it would reach terminal velocity. 40 would be its terminal velocity. But does that?
You're right in that when you include air resistance. it will pick up speed faster and faster and faster till it reaches its terminal velocity. I haven't actually answered your question yet, so give me a couple more in the next step. I'm just building. Are you with me so far? Okay. So, in looking at the motion of this object, we look at its net effect. You guys are right, it's still falling because this one's bigger, its weight, at this point. But the acceleration is no longer just due to gravity. It's not 10 anymore. It's something a little less. Because air resistance is trying to accelerate it up a little bit at this point. So I don't know what the value is exactly, but I know it's accelerating at this point less than 10 meters per second squared. So when it started falling, it accelerated at 10. But it's fallen a little bit, and now it's a little less. As it keeps falling, say down here, the weight doesn't change, but there's more air resistance because it's going faster. Correct? And so this net acceleration of this is decreasing. So the acceleration does not remain constant with air resistance. Thus, the velocity changes by a different amount each second. Yeah, each second it still picks up speed, but less each second.
Because that's what terminal velocity is eventually it's going to come out towards the net force is zero.
Yeah, now the net force is zero because when these two are equal, now the acceleration is zero, so it's gone from 10 to 0, decreased down. Now the velocity doesn't change at all for every second. It just stays the same. That's terminal velocity.
The velocity's gone from 10 to 0.
The acceleration has gone from 10 meters per second squared when you first let go of it, just gravity. But then as it picks up speeds, air resistance increases to the point of terminal velocity. And now the velocity doesn't change anymore at all. The acceleration must be 0. Good job. All right. Whoop. Hello. That was that one. Well, let's see. I had 2 more questions I want to ask you, so let's do it. Polling is open. So a 10 kilogram rock and a 5 kilogram rock, it says one doesn't fall faster than the other. Why? It's in there somewhere. You on channel 44? All right, 10. Everybody hasn't voted that voted before, so I got to count down. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Somebody's not playing. All right. All right, most of you think it's C and D, but most of you think it's D. I'll just reveal it this time. It is D, so the majority got it right. But there's still some confusion. So it's 10 kilograms and it's 5 kilograms. Do you agree they hit the ground at the same time? What's the same for both of them? Okay, gravity. Be more specific. What about gravity? Yeah. What I want to get at is the acceleration the same or the force the same or both? Because there's a difference between force and acceleration. I hope you know that. Yeah, so think about it now. The acceleration due to gravity is the same for both. They get accelerated at the same rate. That's why it takes the same amount of time and they hit the ground together. The one that's heavier, 10 kilograms though, to go at that same acceleration, what's it going to require? More force. That's Newton's first and second laws. Something that's heavier, the 10 kilogram rock, needs more force acting on it to give it that same acceleration. So it has more force on it, but it also has more mass. It's that ratio is staying constant. What is that ratio? Acceleration, you can think another way to think of it is it's a ratio of force to mass. Something that's heavier that requires more force, it's because it's heavier. It's got more mass. It's more resistance. So these go up proportionally, a lot like this one was. So the ratio stayed the same. Acceleration due to gravity is the same for all objects. I'll show you a demo right after one more question we have. All right, let's see if we get this one. Got to think on this one. So heavy ball, light ball, they both feel air resistance. But how does how's that drag, that air resistance compare? Are they the same, more or less? You guys aren't responding as fast. That's good. It means you're thinking. Give you some clues. Okay. The heavier ball, the lead ball, the weight's bigger, right? So there's a bigger downward force. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. All right, half of you think it's A. You're right. To slow it down, its air drag, because it's heavier, the weight's more, it's going to take more air drag. To slow it down, you need a bigger upward force because it's heavier. Which one will reach the ground first? The heavier one. Which one will have a faster terminal velocity? Oh, we got lighter and heavier. Somebody break the tie. Oh, the lighters are breaking. Who will hit the ground first? Then we got the lighter. Well, I should have asked that one. That was the question before this one. It's the heavier. Which one had the greater terminal velocity? The heavier. That means it's going faster. So it's going to reach the ground first because it's going faster. It's going to take longer, require more air resistance to reach its terminal velocity because it's heavier. It's got a bigger down, so it's going to take more up. And it's going to take longer to do that, meaning it's fallen further and picked up more speed. So by the time it gets to terminal velocity, the heavy one, it will be going faster. And because it's going faster, it will reach the ground first. It's easier to slow down the light one because it has less mass, less inertia, requires less force, less air drag. So it'll fall more slowly, reach a slower terminal velocity. Does that help?
Is your second question which reaches terminal velocity faster?
Well, I asked several questions now, but I think my lead-in was who would hit the ground first? Yes?
So lighter objects are affected by air drag more, but then they experience less air drag?
Yes.
Okay.
See if I can repeat that. Lighter objects experience less air resistance?
Yeah, they're affected more by air resistance.
They're affected more by air resistance. That's Newton's first law. Things with less mass, lighter objects, have less inertia. So they can be changed more. So they don't need as much force to affect their motion. So air drag affects them more because they're smaller, they're lighter, less inertia. That part should make sense.
Yeah, but then they're falling slower, so they experience less.
But because, that air resistance is kicked in quicker because it didn't require as much, they're now at terminal velocity and they don't pick up any more speed. So they're falling more slowly,
Okay.
like a feather. Yes?
Question about that. Question on the board.
Okay?
If you dropped an object and you knew its weight, and you wanted to like calculate how when it got to free fall, the air resistance would be changing the whole time, wouldn't it?
Yes, when you drop an object, the air resistance does change.
Yes, it did.
As it falls faster and faster, it increases.
But I mean, the air gets heavier if you weigh up.
That's true too. The density of the air matters.
So that when
For most of what we deal with, it doesn't matter. No, that's right. It would always be changing.
Yeah.
If you started way up high in the atmosphere where it's thinner, there is less air resistance for a given speed than if you did it down here. That is true.
But if you didn't have air, you could probably
If-
calculate.
Yeah, if you didn't have air at all, well, then it's just free fall.
Yeah.
And all we have to deal with is 10 meters per second squared. And it's a lot easier. So things are changing all the time in the real world. But in physics, we try to control things so we can understand that first simplistically. Then we add in air resistance. And then we change the acceleration. Then just to confuse you, right? I think you guys are getting a grasp on this. This is good. You can put your clickers away. I'm done with that. I want to show you. Everybody should see this once in their life. Has anybody ever Googled the astronaut on the moon? Because you can watch it when he drops a hammer and a falcon feather at the same time. There's essentially no atmosphere on the moon, so there's no air resistance. So what do you expect to happen when he drops them? They should accelerate at the same rate, but there's no air resistance to slow the feather down. They should hit the ground at the same time. We never see that here, do we? Unless for things that have a lot of air resistance. So that's what I want to show you. Here's our feather. Here's our ball. You know what's going to happen. Ready? 1, 2, 3. Whoosh. Ta-da! The ball probably never reached terminal velocity because I didn't drop it from high enough, but this one clearly did. So this one kept picking up speed, falling faster, reaches the ground first. Whereas this one was retarded because it has less inertia, reached terminal velocity and just slowly made it down. So now let's get rid of the air, shall we? So I have a little electromagnet here. I can put these on the platforms, and they'll allow me to release them at the same time. So then I'm going to seal it off. And now I'm slowly removing the atmosphere inside, pulling air out with a vacuum pump. So as we get rid of more and more air, there's less and less resistance. I'm stalling now because it takes a minute. And so I'll release it, and you guys can see that I'm not lying to you. If I only pulled out half of the air, let's say, inside, what do you think would happen? Speak louder, this thing's noisy in my ear. So it'd be a closer race, but the feather would still be behind. They'll still hit the ground at the same time, even if I only had half the air in there? Sorry, I can't hear you.
No, they will not hit at the same time.
They won't. Would it be any different, though, than had I not removed any air? And what would be different?
The speed would be a little bit slow.
A little bit slower. Well, let's do the no air and see what happens. I'll get out of the way. All right, watch the bottom half. And you ready? 1, 2, 3. Woo! They do. They accelerate at the same rate. Even the feather fell right along with the heavy ball. If we only had half of the air in there, the feather would have fallen faster than normal out here, but it still would have been a little behind the ball because there's some air resistance. Here I was trying to get rid of most of the air so you could see it. Here's my favorite part, though, of this demo. Letting the air back in. Boom. That sound. I just like that sound.
So if there's no air in there, what is in there?
Nothing.
There's literally nothing.
It's called a vacuum.
It's so weird.
This is, some over, what is it, like 3/8 of an inch thick. I just forgot the type of plastic. It's strong.
Surely there's a constant pressure on anything that has a vacuum, right?
That's right. When I drop the pressure in there, the pressure out here, which we're going to study, is exerting a force on it. And if this isn't strong enough, it would implode. And that would not be safe.
But what is that pressure that exerts?
We call it atmospheric pressure. And pressure is a force acting over an area. It's a ratio of force over area. So the area of this divided into the difference in that pressure. I mean, whatever that difference in pressure is, times that area would give us how much force it's actually feeling. And we're going to cover that in subsequent chapters. So yeah, it is a big force, but this can handle it. I don't use thin wall wimpy stuff. Or little plastic that just crumples. Cool. I did fix my little truck. But I let run off the board. Let's see, time-wise, that was velocity vectors. I think I'll save that for next Wednesday. Use it to teach you a little more about vectors and components. That's at the end of chapter 5. Yeah, so that you have that better. But I want to do more of the beginning of chapter 5 then. Okay, I haven't used this yet, but I bought it. How many of you guys had the little parachute man when you were a kid? All right, let's reach terminal velocity. People in parachutes, they think they land nice and soft. They don't. They still hit pretty hard, but at least they can reach a slower terminal velocity because there's more surface area, and they don't break bones when they land, at least if they bend their legs. So you guys know all about terminal velocity now. So next time you're tossing things in the air, you can tell it reaches and slows down at least before he hits the ground. But there you go. Now you guys have already touched on Newton's third law. Oh no, we better start with this one. I need 2 volunteers. This is my opener. 2 volunteers to help me demonstrate this. We're going to have you come down and sit on these carts. Thank you. And right behind you. Yeah, come on down and get comfy. Sit on one of these boards. You're going to face each other. So as close to this end, yeah. You'll want to roll, so maybe crisscross applesauce, if that's comfortable. Yep. All right. This is to burn into your minds Newton's third law, which is for every action there's an equal and opposite reaction. So if you guys put your hands out, okay, what I want you to be is a wall. You're rigid.
Okay.
Don't move. Okay? And you push off of her. Whoa, I told you not to move. Come back.
Okay, I'm sorry. Okay.
All right, you put your arms out and you're stiff. You're a wall.
Okay.
I am a robot. Wait, you're pushing.
Can I put my legs in the
All right. We'll get your...
Go like this?
Nope, you got to be free to move. This time you be the wall.
Okay.
Let's see. Okay, you're stiff. Push on him. No, you pushed now. All right, I'm just being silly. You can rest a moment. You guys are doing exactly what I wanted you to do, but that's my point. They both moved. You're both feeling a force. If you're exerting the force, you can't help but push back. All forces come in pairs. You can never have a force by itself. If something is acting on something else, then that something else is pushing back. It's equal in magnitude, opposite in direction. So that's why you guys went to two. Right. And it works whether you're pushing or pulling. So you just hold on to it, and you gently pull. But they both move. So, very good. They all come in pairs, action-reaction pairs. So let me point them out to you. She pulls on the stick. What's the reaction to that? She pulls on the stick that way. What's the reaction? What? Very good. A lot of people think it's him. No, she pulled on the stick, so the stick pulls on her. She pulls the stick that way. The stick is what's pulling her this way. But the stick is getting pulled this way, right? She did that. So the stick's rigid. It comes over here, and it pulls on him this way. So the stick pulls on him this way. What's the reaction? He pulls on the stick this way, which is why it stayed firm enough for her to move. Those are the two pairs. And it works whether you have a rigid rod or a rope. I think you guys get it. So now we're going to have more fun. Here, fill this.
Okay.
Fill this. All right, you start. You come up here. I want you guys to toss this ball back and forth to each other as fast as you can.
Oh my gosh.
Good job. Give him a hand. You guys can have a seat. Thank you. Boing. This is 10 pounds. It's a medicine ball. So there, let's do the pairs. She tossed the ball. So she exerted a force on the ball that way. Reaction? Ball pushes back this way. Yeah, there's action-reaction. There's the pair. Then it flew through the air, and it stayed happy, right? Inertia. Until he exerted a force on it. In which direction did he exert a force? Right. What's the reaction? Ball pushes back on him, and so he recoiled. And you saw that. Now, see if you guys were good scientific observers. They both moved. They both reacted. But did they react differently? Did one move more than another? Who moved more? She did. Why? Less mass, less inertia. Right. Very good. That's back to Newton's second law. And first. So, that was this idea we covered last time. Okay, the force between them was the same. The action-reaction. But the big mass was accelerated less for the same force. The smaller mass was accelerated more. Yeah?
Is that why on like trampolines, when if you like are bouncing with somebody that either weighs less or more than you, the person that weighs less always gets bounced more?
That's a good example. Yeah, on the trampoline when you're trying to... Or popcorn's fun.
Yeah.
But yeah, there's also that resonance thing when you land just right. But yes, people with a bigger mass, you come down on the trampoline with a certain force, so the trampoline's trying to react to that by pushing force to everybody on the trampoline. So the small people will change their motion more. And the little people will go flying better. Exactly. Action, reaction. This seems simple, but then for the rest of this lecture and Wednesday and in your text, we're trying to apply it because people still seem to get confused, so I want to think of a few. Here's one. Hopefully these are still good. These are called rocket balloons. They're my favorite type of balloon. They don't pop. So, how many of you, as a kid, you take the balloon, you're trying to tie it, and before you get it tied, it slips out of your hands and goes... That's great. This is like that. Ready? We gotta do that again. So while I'm pumping it up, what's the balloon doing? It's pushing the air that's inside it out the back end. So it's exerting the balloon exerts a force on the air. What does the air then do? Newton's third law, equal and opposite reaction. So if the balloon pushes on the air must push back on the balloon with the same force. I like when it flies over your heads, but you know.
Where do you buy those at?
Oh, just Google rocket balloons. There's lots of toy stores that sell them. Rocket balloons. They are cheap, you know, I won't lie. When you get them, a few pop on you, scare you to death, but they come in a package, so. They make a sound because as the air is pushed out the end here, the flaps come together because there's a decrease in pressure. We'll cover that too. And then they get pushed apart, and so they're flapping like a reed. And that makes the sound you hear, the vibration. Maybe if I start out here. But yeah, things that propel, propulsion, the word thrust, that's Newton's third law. Because if it shoots the air out, the air pushes back and propels the balloon forward. Or a rocket. My daughter loves these too. Let's see, here's a different version. Let's see. Got a helicopter here. We'll put a balloon on this end. All right, this forces it into the helicopter blades. There's little tubes in here. And then they shoot out sideways, tangentially. And this one shoots that way. And this one shoots that way. So again, if the helicopter forces the air out that way, the air pushes back on the helicopter that way and gets it spinning. But then the helicopter blades push air down. That's what airplane wings do. They push air down. Well, if the wing pushes on the air down, the air pushes back on the wing up. That's lift. Let's see if it works. There you go. Oh, where are we at? Let's see. Let's do this one. Nah, I'm going to save that one. That'll be fun tomorrow or Wednesday. Do this. Okay, here's our scale again. It provides a supporting force, correct? Measures our weight. We've been here before. So, okay, I weigh 180 pounds. So, what's pulling me down? Yeah, the Earth is attracting me, accelerating me at 10 meters per second squared down. Multiply that by my mass, which doesn't change, and you get my weight, force down. Okay. So, why am I not falling? The scale is supporting me with that equal force. I'm in equilibrium, I'm not accelerating, and it reads how much force that is. So, what's the reaction pair to my weight? Earth pulls me down. All forces come in pairs. What's the complement? Yeah, the reaction force. What is it? It's not the support force. That's why I'm emphasizing this. And you want to know how I know that? This is what I want to emphasize. Last thing. All pairs, action-reaction pairs, are on different objects. They can't be on the same object. If you push on the ball pushes on you. Notice how they're on different objects? The balloon on the air on the balloon. So this one, the Earth pulls on me. The scale pushes on me. Both affect my motion, so they can't be a pair. So if the Earth pulls on me, what am I doing? I'm pulling on the Earth. I am attracting the Earth towards me with 180 pounds of force right now. Yeah. So next time you're feeling wimpy, just remember that, your weight. You're literally attracting the Earth. So normally I would jump off now, but if I jumped off while I'm in the air, it attracts me with 180 pounds of force down. But I attract it up with 180 pounds of force. Do you believe me?
I do, because I know you're right, but I don't get it.
Well, it's Newton's third law, right?
Yeah.
Earth attracts me. So I must attract it. What's confusing you is... Oh, go ahead.
The reason that the Earth doesn't move is just because it's so big that it doesn't really...
That's the reason. All right, let me redraw this one a little. Okay, here's me. Here's the Earth. It's just because its mass is so big compared to mine. It has so much inertia, we don't see its change in motion. The effect is almost negligible. But technically, it is being accelerated by my 180 pounds of force. But yeah, it's so big, we don't notice it. But we notice what happens to us because we're puny. And so we accelerate at 10 meters per second squared.
So what, as our population grows and there's just more of us and there's just more crap on the earth, we're just attract, you know what I mean? Like,
If we kept adding more and more stuff to the Earth and living on top of it, yeah, the mass would increase.
and
Technically.
that attraction increases as well.
It would, yeah. So the reaction to this, I push on the scale pushes back down on me. But that's that pair. But the pair due to your weight is what I was just mentioning. A lot of people don't realize that, and I think that's kind of cool. You're actually affecting the Earth. A little bit. Okay, you guys have a great long weekend. Don't forget your homework Sunday. Start early. You should have started already. But